Hey guys, so this video is going to be on predicate logic proofs. So that's going to be doing proofs with quantifiers and the 5 new rules we add to just all the rules we keep over from propositional logic. So we're going to still hold on to all our rules like modus ponens, modus tollens, HS, De Morgan's, all the good stuff. But now, and we can still do those to things like PA, to D, B, or something like that, and then if we have PA, then we can get DB. So this would still be an instance of modus ponens. So we're still going to keep all of these over, except now our sentences are just a little bit more fine-grained, right? So now we don't just have to make sure that that capital letter matches. We also have to make sure that we're talking about the same person, right? So if this means Alan is a parrot and Billy is a dog, right? I mean, this would be a weird sentence, but the point is we can't, this is saying if Alan's a parrot, then Billy's a dog. So if our premise is really just PB, if Billy's a parrot, then we can't do our modus ponens because these no longer match up, right? So for all of our old inference rules, we can still do them as long as we just also make sure that the constant matches. So that's going to be the first thing to remember for doing propositional or predicate logic. So proof like this is just going to be really straightforward, just as straightforward as it would have been in propositional logic. So this would just be a single instance of DS. We would be able to get QA from 1 and 2. So, right. But now the idea is the whole point of doing proofs in predicate logic is that we're not just going to have to do, or we're not just restricted to these propositional logic rules. We get more rules, and this allows us to handle arguments like this. So remember, at one point, one of our videos, we looked at a sentence like this or an argument like this. Aristotle is a man, all men are mortal, so therefore I want to say, so the conclusion, I should say, so what I'm trying to conclude from this is that right, very straightforward argument. Now, remember, we couldn't really do anything with this if we were just doing propositional logic, right? So well, first of all, if we could only symbolize it in propositional logic, then everything just gets its own sentence letter, and really there's nothing we can do with that. Oops. And so that's basically all that's happening. Right, if all we're trying to restrict ourselves to is the propositional logic. But when we can do predicate logic, now our sentences are more fine-grained than just a single capital letter. Now we have something like is a man, so we can use, we can say MX means X is a man, and we can say OX means X is mortal. And then we can symbolize a sentence like this. So we can go in and we can take Aristotle as a man. So let me go ahead and move this over, actually. So we can take this sentence and just put it into logic. So Aristotle is a man. So we're just going to take MX, and we're just going to say, and we should also go ahead and define, we need to give a name for anybody that we want to talk about. So A is going to take out Aristotle. And right, so our lowercase letters pick out particular objects, and our uppercase letters are the predicates. And so if we want to say Aristotle is a man, well, geez, we have premise 1 would be 1. Aristotle is a man, right? So MX means X is a man, so MA means A is a man. Aristotle is a man. Premise 2, if we want to say all men are mortal, so this is just one of our A statements, right, from just from Aristotle's list of sentences of A, E, I, and O. And so when we're symbolizing A statements, we're saying all men are mortal, so we want to say for all X, if X is a man, then X is mortal. And then the idea is we want to derive somehow the conclusion that Aristotle is mortal. Right, so Aristotle is mortal. Okay. Now, if all we had were just our basic propositional logic rules, well, there's not really much we can do here, right? Because if we can't do a modus ponens here, because modus ponens, first of all, requires that this conditional is the main operator. And now that we have a quantifier in front, it's the quantifiers that's the main operator. Just in the way that if we had a tilde up front here, then it would be the tilde that's the main operator. So that arrow is actually inside the sentence. And so what we're really concerned with, or the real main operator here, is the quantifier itself. And it's going to be very important to identify when it's the quantifier, which is the main operator. Okay, so the idea here is we are not allowed to do a modus ponens because we don't have any just pure conditional sentence. Modus ponens only works when you have just a true conditional sentence. 2 is really just a universal sentence, right? It's saying for everybody out there, something is true. That something happens to take the form of MXOX, or if MX, then OX, but the sentence itself is not a conditional. But the idea is, remember how these sentences work. So I'm going to go ahead and erase the original English because we don't really need it anymore, or the word bag. So let's just focus on the logic at this point. Okay, so I'm going to go ahead and scoot this over as well. So remember what's going on here when we're doing predicate logic. We always want to have just a list of objects in the back of our head, and then one of those objects, in this case, is Aristotle. And maybe there's a bunch more objects that doesn't really matter in this case. I mean, because we're only really talking about Aristotle in this proof. But the fact that there's a list does matter. It just, we're not concerned with any other particular person right now. Okay, so the idea is MA is just saying that the sentence, right, MA is true. It's just saying Aristotle is in fact a man. And then 2, remember, is saying for everybody on this list, you can check this sentence for them where you substitute X for their name. So if this is B, C, D, E, F, right? So everybody has a name. We're just, again, not concerned with any one of these particular guys right now in this proof. But the idea is we still want to get a hang of thinking through these things as checking a list in various ways. So when we have a universal sentence, we need to make sure everybody on the list satisfies this sentence when we substitute out X. So we need to check MB, arrow, OB. We need to check MC, arrow, OC. Right? We just need to check for every person. We're just going to substitute the same name. And that also goes for A, of course, up here. And so the idea is, remember, in an argument, or when we're trying to prove something is valid, we're going to always assume that the premise is true. we're assuming that both of these guys are true. So the idea is, if I'm assuming that this is true, I'm assuming each one of these are true. Right? So that means I already know, just based on this being a premise, I already get this guy for free right here. Right? The MA to OA. Right? Put OB there for some reason, right? That constants have to match. So the idea is, this gives us our first predicate logic rule, universal instantiation, which is just a fancy way of saying I'm going to take a universal sentence and I'm just going to give you one instance of that universal sentence. So in this case, I'm going to take this sentence that for everybody, if you're an M, then you're immortal. If you're a man, then you're immortal. And I'm just going to give you a specific instance of it. And I can choose any instance I want. I can choose absolutely any instance. I can do it 1,000,000 times if I wanted, just for everybody on the list. But the idea is, I want to be smart and think about what is actually going to help me here. And choosing it for something like MB to OB, or right, to OB, that's not going to help me, right? There's nothing, it's not like I can do any more rules with that. But if I chose something like MA, gives me OA, then that means, so let's go ahead and move the conclusion off to the side where it belongs. So if this is the line I derive for my new rule, universal instantiation, from line 2, now I do have a perfect match for modus ponens, right? Now I do have green on the left. Oh, look at that, I actually have green. And so now I can actually give myself the right side, right? So once this is, we're checking this modus ponens now that we actually have this line 3. So once we've done this UI right here, now we actually have the modus, or this new conditional line, and then we can do a modus ponens, right? So first, let's make sure we're doing this slow enough so people can see. So all we're doing right here is we're just saying, okay, you're telling me that this sentence is true for absolutely everybody. So instead of talking about everybody, I'm just going to talk about it for just one person. And that's just called universal instantiation. Okay, and now on the next line, now that we have that line, and the reason why I wanted to talk about it for Aristotle is now I can do a modus ponens. Now this matches up. It's saying if Aristotle is immortal, then, if Aristotle is a man, then Aristotle is mortal. And then line 1 says Aristotle is a man. So that's just a perfect match for modus ponens, and so I can get OA, modus ponens, 1, 3. Right? So this is one of our new rules, UI. And the idea is it lets us go from a quantified statement to a non-quantified statement. And that's the only way we're going to be able to do our old school logic rules. Okay, so another way this could happen is if, let's see. So at other points in proofs, for instance, like let's say so that's how we take off the quantifier. But let's say maybe our conclusion is something like, there exists someone that is mortal, right? And then let's go back to our old, oops. So if you're paying attention, you already saw I made a mistake there, right? To say there exists an X such that AX, that's saying there is somebody such that Aristotle is mortal. That actually isn't as big of that's not a violation, because I don't have a free variable. I just have this extra quantifier, this group of people that I never refer to if I keep this as an A. So the idea is if I want to refer to that group of people, then I need to use that variable I introduced, right? So this is saying someone is immortal, is amortal, right? And so if we go back to the same premises, so mx ox. Again, now we should be able to see this is also a valid argument, right? If I assume that Aristotle is a man, and I also assume that all men are mortal, then I should believe that somebody is immortal. So the first thing I'm going to do is, well, I mean, we can just think through this reasonably. Why do I know that somebody is immortal? Well, first of all, I know that all men are mortal. And because Aristotle is a man, he's got to be immortal. So basically the idea is I've found somebody that's immortal. So let's think about that in the sense of finding in our lists. So remember what this sentence means down here is that you can go down. So remember what this quantifier means. It just means you can go down the list and for at least one person, this sentence is going to be true. So that means we're going to be able to go down the list, and it's not the universal, so we don't need it for everybody. But it means we can go down the list and we'll ask, okay, Aristotle, are you an A? Billy, are you an A? C, are you an A? Or excuse me, Aristotle, are you an O? Billy, are you an O? C, are you an O? Are you mortal? Right? For each of these, we're just going to plug in that constant into the sentence and just ask if it's true. And because it's just an existential quantifier, we just need somebody to say yes, right? We just need one person to say yeah. And so the idea is I can prove this if I can just find somebody that says yes. So you might already see where we're going. Well, I already know, like the objective now is just, okay, how can I figure out who is actually going to say yes to being an O? And you should be able to see from right here we're going to be able to determine is going to say yes. Because here we have that A says yes to being an M, and then line 2 says anybody that says yes to being an M is going to say yes to being an O, right? So now all we have to do is just formalize that a little bit. So, but the idea at the end of the day is we're just going to, you want to know that somebody is immortal? Well, Aristotle is immortal, so I'm just going to bring him out, and then we'll be able to get to our conclusion. So the idea here is we're going to go ahead and instantiate 2 just the same. So we're going to go ahead and do MA to OA, and that's going to be another universal instantiation from 2, just like before. And now we can do our modus ponens, just like before. So 1, 3, modus ponens. And now notice this still isn't exactly the same as our conclusion. And remember, the only way a proof is happy, the only way you've really proven that an argument is valid is if the last line of that, if the last line here is actually this guy. That's what it means to prove something is valid, right? So the idea here is from just knowing that Aristotle is immortal, we can deduce now, and this is the idea behind just what it means to be an existentially quantified statement, that somebody is immortal. Okay. And I mean, that's definitely not something you, so this here is a new rule right here. And I will slow down in a second and recap both of these together. But the idea here is existential generalization is what this is called, e.g., and we're getting this from 4, is, okay, here we're talking about a particular person being mortal. So anytime that happens, anytime you know a particular person on this list is being mortal, you know somebody is being mortal, right? Because that's all that it means to say there exists an X such that OX, is to say that I can go down this list and eventually I'll find somebody that is in fact a mortal, that will say yes to that question. Okay, so e.g. just lets us go from any sentence that has just a constant in it. We can throw away that constant and put in a variable and then use the existential quantifier. So the idea is anytime we know a specific guy is doing something, we can take a step back, and instead of being particular, we can just be a little bit more general and say somebody is doing something. And so that's why we call this rule existential generalization. Okay, so let's just look for a second at what's going on here. The first thing we did in this proof was we tore off a quantifier, right? The last thing we did here was we actually added on a quantifier, right? So first we went from a quantified statement. Let me use the, so first we went from a quantified statement right here, and then we ended up with an unquantified statement, right? So we're tearing off. That's due to this sort of thing when we're finding an instance, right? And then the other thing we did was we came from an unquantified statement without any quantifiers, to one with quantifiers. So we generalized. We got, so for the pink one, we got more specific. We found an instance. For the generalizing rule, we got a little bit more general, and we found, and we're just talking about, I know somebody is a mortal, right? Okay, so this is just important to note this right now, and we'll talk about this more in just a minute. But the idea here is sometimes we're going to be tearing off quantifiers, and sometimes we're going to be putting them on. Okay, and sometimes we're going to be doing that to universal quantifiers, and sometimes we're going to be doing that to existential. So ultimately, we're going to be able to do UI, but also UG, and we're going to be able to do EG, but also EI, right? So we're going to get all four combinations. We're going to be able to tear off and put on any quantifier we want. And that's 4 out of the 5 rules right there that we're going to introduce, and then we're all done. And the 5th rule I've actually already shown in the translation video, so if you understood that, then we're okay. But let's go ahead and slow down and just also, I want to point out something else going on in this proof. Okay, so generally speaking, what typically happens in these proofs is they come in 3 phases. Okay, so the first thing that we do is we're going to figure out how to tear off our quantifiers. All right. The second thing that we do is basically just old school logic. Okay. And the third thing that we do is add the quantifiers back on. Okay. So this was a super simple proof, and typically you don't have just 3 lines where just it's 1 line a piece for each of these stages. But generally speaking, it can be very helpful to think about this in just 3 stages of, first, let me try to get rid of my quantifiers, so that way I'm talking about some specific stuff. And that way you'll be able to do a lot more old school logic. You'll still do some old school logic in here sometimes. But the idea is you're first going to want to tear away your quantifiers, and then you can really just finish anything you need to do with old school logic. And then if you need to, notice in the first example we didn't need to tack on any quantifiers, but at the end of it, we'll go ahead and generalize somehow. We'll say, okay, that means somebody is doing it, or sometimes that means everybody is doing it. So that's just a quick observation, but this is all stuff we'll look at as throughout this video. Okay. So, as I mentioned, there's 4 new rules basically that we have, right? So, let me go ahead and make that rule. Okay. So there's that, and then we do that. And that. All right. So, well, actually, let me make those a little longer. Oops. Okay. So the idea here is we've got two different types of quantifiers, right? We have the universal and we have the existential. Right, so that's going to be just okay. So we've got the two different quantifiers, and in addition to that, we also have what we want to do with those quantifiers. So we can instantiate, or we can generalize. Okay. So when we instantiate, what we're doing is we're taking off or we're removing. Let me say that. And when we generalize, we're adding it on. Okay. So that said, let's go ahead and just look a little bit closer at really what's going on here. So the idea here is when you're doing a universal instantiation, so let me go ahead and put in the names of each of these rules. So we can do a universal instantiation, or we can do an existential instantiation, or we can do a universal generalization, or we can do an existential generalization. And so the idea is whenever we're doing an instantiation rule, we're removing a quantifier. And whenever we're doing a universal rule, we're doing it with the universal quantifier. So if we're doing a universal instantiation, we're going from a rule, or we're going from a line that has a universal quantifier, like this, to a line that doesn't. Right? But if I throw away that quantifier, I can't use X anymore. I need to be talking about a specific person, right? The sentence just FX, right? If I just had FX, that doesn't mean anything. Who are you talking about? You're not telling me how many people you're talking about, and you're not talking about any specific person, so that doesn't mean anything. Okay. So the idea here is anytime you're doing a UI, we're going from a sentence that's talking about everybody to a sentence that's talking about somebody. E.g. is the other rule we already saw, and so that's going to be when we're adding the existential, right? And so that's when we don't have, that's when we have a line without a quantifier, or at least it has a constant. So we'll talk about complications in a moment. And we go to a line with a quantifier, or at least with another quantifier. So in this case, because it's existential, we do this. Right, so the idea here is we're going from a sentence like Aristotle speaks French to, oh, that means somebody speaks French, right? Here we're going from everybody speaks French to, that must mean Aristotle does. Okay, so there's, I mean, these rules should make good sense, right? If you know you can check everybody off your list as saying yes to that F question, then that means the first person, Aristotle, must have said yes to it also. On the other hand, if you know that Aristotle said yes to that question, So, you know, if Aristotle, it's true that FA, then it's true for somebody. And oh, look at that. I've already made a mistake. I've warned against doing it, right? So this, again, that's not, we know it's not just that there's somebody, that's Aristotle. We're trying to be more general, right? So we're saying there exists an X such that he, right? So when we do a generalization rule, we're throwing away the constant and adding on the quantifier. Sorry about that. Right. So generally speaking, right. So we're always going to go from a sentence that has a constant, and we're throwing away that constant and adding a quantifier for the new variable. Right. We're swapping the constant out for just a variable, and then introducing that variable with some sort of quantifier. Now, I mentioned a couple of times that there might already be a quantifiers for one of these sentences. So, like, if the sentence is something like, there exists an X such that X is a man and Aristotle is a man, something like that. I mean, this sentence still makes sense. It's saying there is somebody such that he's a man. Oh, and also, side note, Aristotle's a man. Okay, so that sentence is still a fine sentence, and nonetheless, we can do existential generalization to it. We would just have to add in a new variable, right? So X is already being talked about here. So the idea is we don't want to get confused. We're adding in, every time you do a generalization, you're talking about a new group of people. So the idea is, here you know somebody's a man and Aristotle's a man. So now you know there exists a Y. We're going to grab a new variable. And there exists an X such that MX, and now we're going to throw away wherever the constant that we had, the one we're generalizing from, we're going to throw that one away for our new variable. Okay. And it also, just to be clear, so just to sum up, it doesn't matter that we had a quantifier. All that mattered is that we had a constant that we were trying to get rid of. And we do that by swapping it out for a variable and adding a new quantifier. And now, just to be clear, even if the sentence is something like, well, let me go back. Even if the sentence is something like MA and OA, you can still do the generalization here. But the idea is you need to throw away the constant wherever it applies. So if you're saying Aristotle is a mortal man, you need to be talking about, okay, that means somebody is a mortal. Oops. And of course, we keep making that same mistake. And this is an A up here. And this is an A. So, right, so we're throwing away those A's for X's, and we just need to introduce how many people we're talking about. Okay, and so because we're doing an existential generalization in these cases, we're just talking about somebody being a mortal man. Okay, so those rules should feel very innocent because, in fact, they are innocent, right? You can think about it in terms of the lists we always go back to, right? If you know, so in terms of, in terms of UG, or excuse me, in terms of UI, that's just saying, okay, well, there's a list of people, and I'm starting off with this sentence. I'm starting off with the universal. That means I already know it's true. I already know it's true for everybody. I know that's true. I know that's true. Right? I already know that's true for absolutely everybody. So it shouldn't come as any surprise that I can just give one instance of it being true. Right? That should be very, very mundane. And then in the other corner, this should also be mundane too, right? So if I know, maybe I don't know that everybody's saying it's true. Maybe some people have even told me it's false, right? But as long as somebody, maybe A is down here or something, I don't know. As long as somebody's told me it's true, that's all that it means for that quantifier to be happy. It's just, yeah, I just need one person to report yes. So these two rules, totally safe. Okay. On the other hand, we have these next two rules are a little bit more difficult. So I mean, first, as you're getting comfortable with this, I would recommend first making sure that you're comfortable with just what's going on with these two rules, because these ones, they're going to work absolutely anytime and every time. So for that reason, I'm even going to go ahead and put a nice green box around them. So they're completely safe. Okay. These other two rules, on the other hand, we're going to need to watch out for. And if you're paying attention, you should be able to see why. Okay. So these other two rules, so existential instantiation, you'll at least be able to guess what these look like. The idea is just kind of getting a grasp for why they work, or at least when they work. Because so for existential instantiation, right, we need to go from an existentially quantified statement, somebody speaks French, to a statement like A speaks French. And then for universal generalization, right, we're going to need to go from an unquantified statement to a quantified statement, right? I'm going to leave that blank until we get to it. But the idea is, let's first look at existential instantiation. So these rules that I have a red box around, these are what we call restricted rules. And the idea is we need to make sure of something. We need to check that we're not violating a restriction before we can actually do these rules. So here, if I'm trying to say that I started off believing somebody speaks French, and I'm trying to get to, that means A speaks French. Well, let's think about that. Here's the list of everybody in my domain, everybody in the world I'm thinking of. And all I know, all I'm starting with is that somebody is reporting T. Somebody. But I don't know who it is, right? This sentence doesn't tell me who is reporting T, right? The sentence that tells me who is reporting T would actually look like, right, FA, or just whoever it is. It would be FB if it was B. But the whole point of the existential statement is we're not sure which one of these guys is going to report T. Somebody is, but we're just not sure who. So the idea is, I can't go just asserting that, so let's say we've already been talking about these people, A, B, and C, or something like that. You know, A is Aristotle, B is Billy, and then C is Chrissy. So let's say they've already been maybe somewhere else in the proof, or we've already been talking about them. The idea is, I can't just go saying, because somebody speaks French, that means Aristotle speaks French. I need to come up with a completely new name when I do existential instantiation. So I need to come up with, I'll go ahead and just come up with something much further down the list, something like, I don't know, K. Maybe K hasn't been used. And the idea is, K isn't anybody that I actually know. I'm just naming this guy. I know somebody here is going to report yes. So I'm just, for the time being, giving him the name K. And then later on, if I find out who it is that's reporting yes, I'm going to say, oh, well, like if it was Aristotle that's actually the French speaker, then, I can't immediately say that they're the same. But the idea is, I'm just providing a new name. Maybe this guy will end up with two names at the end of the day, but I'm just providing a new name. All right, and so like the intuition here is, like, if we're talking about, right, I don't know who invented the TV, but I mean, if we want to talk about him, we can kind of just give him a temporary name for a second, just so that we don't have to say the guy who invented the TV. We can just say, well, let's just call him Tom, or let's just call him Ken, because we're using K here. We can just say Ken was a really smart guy, right? Because he invented the TV. And if you have another premise that says anybody who invents the TV must have technical know-how, well, then you know Ken has technical know-how. So we can start doing, right? We want to tear away those quantifiers because we want to be able to do those inference rules. So the idea here is we're just going to give a temporary name to whoever actually is the somebody who speaks French, right? There might be more than one person who speaks French, so we're just giving a temporary name to just at least one of those guys, right? So, but the point here is the restriction. Let me write this over here. It has to be a completely new name. So it cannot be a constant seen earlier in the proof. Okay, so if we're doing a proof and one of our premises is PA, another one of our premises is PB, and later on maybe we want to do an existential instantiation to some other line, I don't know, QX, there exists an XQX. We can't just say QA. That's wrong. We also can't just say QB, because the idea is we've seen B and we've seen A before. We need to just scan everything north of the existential instance rule and just grab some new line, or just, excuse me, some new constant. So in this case, we grabbed K. So I want to make sure that that K looks sufficiently different than the X. Right. So, but that's the idea, is we're grabbing a totally new constant. In this case, it's K. Maybe K isn't the best. Maybe that's too far down the alphabet. You're going to start thinking about it as a variable. So let's just say that you haven't seen D yet, right? So as long as you haven't seen that constant yet, you can use it. Okay, so I'm just going to leave D there, because it is important that you choose a constant. You can't leave it as a variable, but you just can't choose a name that you've already seen before, because you don't know it was that specific person that's the somebody that this premise is giving you. Okay. I know that might feel like a little bit of overkill, but that's kind of what happens when we have these restricted lines. Okay. So that's existential instantiation. Just because you know somebody did it doesn't mean you know who did it, so you need to make sure you're coming up with a new name when you're trying to specify, when you're trying to do logic with it. It might not be totally clear why you would want to ever come up with a totally new name, and that's fair enough right now. When we get into the proofs, you'll be able to see better. At times, it'll be nice to be able to say, just talk about a general person. Right. So, okay. So we'll get into that when we get into examples. Okay. So universal generalization is the next rule that we want to look at. And the way this rule works is, of course, it's a generalization rule. So we're coming from a line with a constant, like FA, to a line, oops, of course, not with that quantifier, right? Because it's a generalization, or it's a universal rule. We're interested in the universal quantifier. So a generalization rule will generalize from that constant. We're not going to want to talk about A anymore. We want to talk about everybody now. So we're going to swap the A out for X, and now we're talking about everybody. And just like EI, this rule should feel a little bit funny, right? Because the idea here is you're trying to go from this sentence that just tells me, I don't know, Aristotle speaks French, to everybody speaks French. So you're trying to go from being able to, so I'm going to scoot this to the side just a bit. So you're trying to go from being able to tell me that just this guy told me T, you know, that true. Like this guy, yeah, it's true that F is an A. But I haven't even asked everybody else, but you're trying to say that everybody is. So the only time that this rule is ever going to work is if this constant is what we call an arbitrary constant. So the idea, the restrictions we have to watch out for here is that the constant that we're generalizing from didn't come from a premise and also didn't come from EI. So we want to say that the constant your so the constant doesn't come from either a premise or EI. Okay, so this might still feel a little bit weird right now, like I'm not exactly sure when that's going to come up. What do you mean it doesn't come from a premise or EI? Well, so it comes from a premise if that constant appeared in the premise. So for instance, right here, if we're trying to do a UG on FA right here to get to for all x fx, we're not going to be able to do it if one of the premises has A already. If this constant appears in any premise, then that means he's not general. That means we already know the specific guy, right? And this concept I haven't really made too clear yet. But the idea is, if a constant appears in a premise, then right, we're talking about a specific person, and from there we can't just say, oh, that means everybody is that way, right? We just know one guy is that way. That's not enough to know everybody is that way. So the only times this is actually going to be safe, maybe a better way to say this is, well, so there's a couple, the constant has to be introduced as, well, so the simplest way is if it's introduced by UI, right? So one way that these proofs go is, if we know that everybody is a certain way, then we can just talk about just a generic individual that is that way. Okay, and if you can find something is true just about the generic individual that is that way, then you can generalize back and tell me something else, right? So let's think about this in terms of an example. I'll go ahead and erase this list for you. Okay. So if you know, okay, so if you know that everybody is a P, and you know that everybody that is a P is a Q, and you want to conclude that everybody is a Q, right? That's what we want to do at the end of the day. We want to get to everybody being a Q. Because we know everybody's a P, and we know anyone that is a P turns out to be a Q, then we know everybody's a Q, right? So if we know everybody is a dog, and we know all dogs are mammals, then we know everybody's also a mammal. So this should be an intuitively valid argument. But it's not like we can do like modus ponens here, right? Because if you're paying attention earlier, or if you were able to absorb it that fast, the conditional is not the main operator, right? So this is not an if the left side, then the right side, because then you're breaking up these parentheses, and we can't do that, right? So it's this quantifier is looking at this entire thing. So we would need to get rid of the quantifier before we do any sort of modus ponens here, right? So let's go ahead and do that. So the way this works, we want to prove this, is we're going to just talk about a generic individual. So we haven't talked about anybody specific in this proof yet. So I'm just going to grab the name A. And I'm just going to say A, let's just call him Albert. Albert is a P. And the point is, there's nothing special about Albert other than the fact that I got him from this line, other than the fact that I know he's a P. So there's nothing special about it. He's a completely generic individual. Everybody's a P. So I'm not making any special claims about Albert. So that means next, when I do, I can do another UI, right? Because UI is always good. So let me also say about Albert, well then, if Albert is a P, then Albert must be a Q, right? So this was UI on 1, and this is UI on 2. So 1, 2, 3, 4, right? And now we can do a modus ponens. Now I can actually do, boom, 5. Albert is actually a Q. So this is finally modus ponens on 3 and 4. Right? And now look, I'm still not at my conclusion yet, right? I know that Albert, this generic individual, is a Q, but I don't know that everybody is. But let's think about this for a second. There was nothing special, right? That's the whole fuss I made. There was nothing special about Albert in the first place. So basically I'm saying this is going to hold for anybody. I can do this same argument for absolutely everybody on the list. So when you get the constant through something like UI, then it's okay for us to do a UG at the end of the day. Okay, and so that's going to be one of the two main, if not only, ways that we're actually going to be able to do UG is if that constant came from a UI. The other way we're going to be able to do it is if we had something like a subproof, like a CP, that started with PA, and this A is completely new. Like when you assumed this, you're just assuming, again, a completely generic individual that didn't come from a premise and didn't come from EI, and you can get to QA. If you can do this, right, that's what CP gets you, then you can do your UG. Right, and so that's the other main way it'll happen. And we'll look at examples of that, or I'll try to remember to bring up examples of that when we get to more of the examples portion. Right, so those are really the two ways that you're going to be able to do UG, or at least that you should be mainly thinking about UG, is that so not only can it be via a UI that you get it, but it can also be so not introduced by, not as. Okay, so we're going to call this a discharged assumption. So the idea there is, let me go ahead and grab that. I don't know if we'll actually set that to the side. Okay. I really wanted to make this big. That's the idea. Okay, cool. So the idea here is, and I apologize for not having the time to edit all this out. But so the idea here is we're able to do the UG down at the bottom here because, again, this A, it didn't come from, I'm just telling you, it didn't, just pretend I showed you here, well, here are the assumptions. Do D or something for all X, P, X, right? I'm not making a full argument right now, but the point is, you're able to do a UG when the A is just given by an assumption in a subproof. Now, what we can't do is if you're still inside this subproof, you can't do a UG inside the subproof. So that's why we call this a discharged assumption. The idea is once you're outside of the subproof, if this A is still around and the only way it popped in was because it was, you just threw it in as an assumption in the subproof, like this is the first time you've ever seen it, and it's still sticking around outside of the subproof, well, then you can do a UG to it. That's how, so that's the other way that UG is going to work. So you either need it to be given to yourself by a UI, or give it to yourself by assuming it in a subproof, ending that subproof, and then you can do UG after the subproof is ended. Okay, so hopefully that's all. Hopefully that's all relatively clear. And the beauty about this is you can kind of review this. I'm going to clean this up a little bit. Oops. Because I know it might be helpful for you to just take a screenshot of whatever is here. Okay, so right, just to recap on this, we have just instantiation rules, and we have generalization rules, we have universal rules, and we have existential rules. But instead of just thinking about that as just a long list of stuff, you either are going to add a quantifier or you're going to take one off. And you're either going to do that to a universal or you're going to do it to an existential, right? So remembering what the four things you should do, what four things you're able to do should be really straightforward, right? You're either going to add or you're going to take off, and it's either going to be the existential or it's going to be the universal. That should be really straightforward. The only thing that might be a little tricky is just remembering what the restrictions are, or which ones are restrictions. So it shouldn't be too bad to remember that these two, UI and EG, aren't restricted, right? So especially if you have this square in mind, just remember they sit on a diagonal, right? The ones that are restricted are on one diagonal, and the ones that aren't restricted are on another diagonal. However you set this up, that's going to happen. Even if sometimes instantiates on the bottom and generalize on the top, it'll still happen. They'll always be on a diagonal from each other. So the idea is when you are removing the universal, you're just getting more specific. And whenever you're getting more specific from a general statement, that's always safe, right? Or if you already know that somebody did it, if you already know that Aristotle speaks French, it's completely safe to say that just somebody did. The ones that are going to be tricky are just going to be remembering the EI and the UG. But just the EI shouldn't be too bad. Just scan make sure that the new constant you give yourself is not found already. For UG, you need to just make sure whatever constant you're throwing away didn't come from a premise, it didn't come from an assumption you're still inside, and it didn't come from an EI, right? You didn't instantiate it from an existential sentence. Maybe you instantiated it from a universal. That's okay, because that means everybody did it. But you can't do it just because one person. You can't generalize back from that. You can't do an EI and then a UG. You can do an UI and then a UG. Okay. I know that that's all a lot of information, but I mean, again, I'm really utilizing the fact that you can slow this down and rewind and watch this however many times you want. Now, real quick on this, let me just throw out one last thing that's good to remember when you're doing these, and that's for this top right rule EI. The idea here is so remember what I mentioned about the way that these proofs typically work. So we're typically going to have one phase where we're trying to tear off quantifiers, a second phase where we're doing old school logic, and then a third phase where we're doing some generalization rules. So now it should be a little bit more clear maybe. So we've got, in first phase, we're going to do mainly instantiate stuff. Not just like this isn't going to be hard and fast. Sometimes you are going to need to do old school logic in here too. And we'll see. I'll try to do some examples of that at the end. But it's really going to be in this second region is where you're working towards, where you just don't have any quantifiers. And this is really where all you can do is old school. And well, really what I mean by that is when I say old school logic, I just mean propositional logic. So that means you're basically going to just have constants and predicates, and you're just going to be doing De Morgans and modus ponens and all that good stuff. And then, right, in the last, you're finally going to generalize. And again, it's not just going to be generalization. It's going to be a little bit more like quantifier negation, which we'll look at in a second. But this is kind of a good mindset to have, is that think about it in three phases. You're going to want to tear off your quantifiers, do some logic without the quantifiers, and then put them back on. Okay, so now the idea though is because these are your because we're going to want to do instantiate rules, basically a lot of times we're going to want to do a lot of instantiate rules right next to each other because you're tearing a lot of quantifiers off all in this first phase. So for instance, if you have a sentence like everybody who's a P is a Q, and then you have a sentence that says somebody is a P, right, and then you just want to get to the conclusion somebody is a Q. Then, well, let's just think about this. So in this first phase, we can think about just trying to tear off the quantifiers. So we're going to want to do instantiate rules, right? So, so the idea here is, let's do those instantiate rules. So we want to do a UI and an EI. So if we just do this in order that the premises are written, then, well, UI, so we're just going to grab a random constant. We don't have any on the table, so there's really doesn't make a difference what we choose. We just have to take that sentence, right? So let me slow this down. I made a mistake there anyway. Basically what we're going to do, anytime we do an instantiate rule, we're just going to take that exact same sentence. Well, it's good to think this slowly. And then what we're going to do is we're going to erase first the quantifier. Oops. So first we're going to erase the quantifier, and then we're going to erase the variable that quantifier introduced. And the idea is so anytime that variable popped up, we need to erase it, and we need to substitute it with a specific name. It has to be the same name every time. Right, so I didn't need that parenthesis. Right, so that's going to be universal instantiation from 1. You just throw away the quantifier and replace the variable with one name for every instance of that variable. Right, so if everybody that's a P is a Q, then if Aristotle is a P, then he's a Q, or if Albert, or whoever A turns out. Okay, so that's just UI on 1. So that's 3. And now if we want to, okay, so we tore off that one. So now all we need to do is we just need to get PA, and then we can do a modus ponens and stuff, and then tack on the quantifier. Cool, this will be great. But recognize that this is a problem. We messed up. We can't do an EI here, right? Because EI, remember, go back to, let me do this one. EI, remember, is restricted. So you can go ahead and check UI, is that restricted? No, UI is totally fine, right? But EI, on the other hand, is restricted, right? And so we need to first make it, when we're doing this, we need to make sure, am I breaking the restriction? So let's ask, cannot be a constant seen earlier in the proof. So is this a constant we've seen earlier in the proof? Yeah, right there, right above it. You just did a UI for that. So what does that mean we do? So you might think, oh, then let's just, instead of doing that one, let's just do B. Well, that's fine, but now you can't do your modus ponens anymore. What you really need to do is now you need to do the UI again, but for PB, arrow QB. So really, I mean, and that just kind of makes this line just basically worthless. So the point is, what's going on here is anytime you need to do two instantiations like this, or you need to do an EI and a UI, and you need to do it on the same variable, always do EI before UI, okay? So you always want to make sure, so the reason why you would want to use the same variable is you always want to make sure, like generally speaking, you want to make it so that your sentences agree with each other, right? When I'm instantiating these two things, I don't want to make it so that I have PA, QA here, and then PB, right? I can't do modus ponens there. I mean, think about it like a Latin language, like a Romance language, like Spanish or something. Their endings just don't agree. You need to make sure their endings agree if you're ever going to do these rules. So right here we have an A, here we have a B. So they disagree, so we can't do modus ponens. So the problem is we want them to agree. We want to use the same constant, but when we tried to do right, so this one was the UI. Sorry, this one was the EI. Right, the UI comes from the universal, the EI comes from the existential. Okay, so right, so the idea is we want these to agree so that way we're able to do the modus ponens, but we can't make the EI take the same constant that the UI takes if it's already seen that the UI took it. So I mean, the solution here is actually really simple. You just do the EI before the UI, right? So all we're going to do here is literally just grab this and move it below this guy. Okay. And now, I mean, why does that work? Why does that make sense? Why is that not just some arbitrary, you know, silly stuff we're doing that? Well, the point is, and okay, so first of all, we wanted, the whole reason why we did this was we wanted to be able to keep these things agreeing. And so now we can have the EI come first, then the UI. So the point is, right, so now we can actually do the modus ponens here. Okay, so the point of all this was, the point we wanted to switch these orders was that EI was not able to take the same constant that UI takes if EI comes after UI. So we need to make sure EI goes first. Right, and so again, yeah, right, so we can think about this. 2 is saying just somebody is a P. And so first we need to say, okay, let's just give that guy a name and say, all right, Albert is a P, right? Or A is a P. And then UI, that's fine with taking, like, that's going to be true for everybody. So I can say, oh, well, if Albert's a P, then Albert's a Q, right? Like, because that's going to be true for absolutely everybody. But if I had that reverse order, then first I'm just grabbing a name with UI and I'm saying, okay, I know if everybody's a P, then Q, or then everybody's, sorry, I know for everybody out there, if you're a P, then you're a Q. So let me just grab a specific name. If Albert's a P, then Albert's a Q. But now, think about it. Now, that guy is just a generic guy that could stand for anybody. So if we had the UI first, and, right, so this is, so if we had the UI first, up here, then that A, you've introduced him as somebody that could stand for anybody. So in the next line, if you tried to do an EI, you're saying, oh, and Albert is also a P. But that's not, you don't know that, right? Albert, if you did the UI first, Albert is just some general guy. So the idea is we need to first introduce him with the EI, and that way, the idea is the way we know Albert is he's that guy we introduced as the P. And now, again, UI doesn't care about how many times it's seen it before. So now we can do our UI, and finally we can do our modus ponens. Okay, so modus ponens, we finally get QA. And then we can do, so we're going from a line without a quantifier, and we want to get to a line with a quantifier, right? So what does that look like over here? So, right, we're going from just that line to that line, right? It's the same exact thing, except for now it's G's instead, or Q's instead of F's. And then just ask yourself real quick, is this restricted or is this safe? And it's completely safe, right? It doesn't matter that I got this from EI or that whatever I've done to it, because e.g., I can do it to absolutely any constant I want. If I already know somebody, regardless of if this was an arbitrary guy or whoever, if I already know somebody's a Q, then, well, somebody is a Q, right? So the last thing we're going to do here is just there exists an X, QX. And that's just going to be EG. That's modus ponens. So EG is going to come from 5. Clean that up a little bit. Right, EG is going to come from 5. These are obviously going to come from their respective lines. And modus ponens is going to come from. So right, it is good, I guess, that I fill in this just in case anybody's not seeing it. Modus ponens, right, that has nothing to do with lines 2 and 1, right? Modus ponens only takes in 2 lines, just a conditional and the left-hand side of that conditional. It's just the green and the red and the green. The green giving to the red and the green, right? So that's going to be 3, 4. Okay, so that would be the last line of the proof, this line 6, getting it EG from line 5, and therefore we get our complete. Okay, so that's going to be an important thing to watch out for. Always EI before UI when you're using the same constants. So that's going to be very important to watch out for. Right. Just one quick tip on the generalized rule before we move on. In order to watch out, and so oftentimes generalized will come up in the case of, so existential generalized, as we just saw, was completely fine. So existential generalized was completely fine to do because, right, it's a completely safe rule. But universal generalized, what if that's our conclusion? Well, oftentimes I think, so one way you might be able to get to that is if you could get with some just generic individual, FA, and then you would do a UG, right? But then the worrisome part is that you just have a lot of restrictions. There's some very complicated restrictions that you have to watch out for. You need to make sure it's not in a premise. You need to make sure it's not from EI. I mean, I guess it's not too complicated, but maybe it's hard to grasp as you're just starting to get used to this stuff. So instead of trying to go that way, one common thing that I think may be useful is if you just do an RAA. Right? We're just going to suppose it's not the case that, thanks. Right? I mean, RAA, it's just, this thing still work, right? We're keeping all of our old school propositional logic, right? This just is P, right? It's just one sentence. It just means everybody, like if we were doing old school logic, we would have symbolized that with just a single letter, P. And so if you want to prove that P is the case, then you can suppose P isn't the case. And from there, we can start to do other things. And so one thing we can do is, well, if you know it's not the case, or if you're trying to suppose that it's not the case, that everybody is an F, well, that means there must be somebody that isn't an F, right? And we'll look at this just in just a minute. But then now we have an existential sentence, and we can actually start working. And it's going to be easier to deal with the EI rule. Like those restrictions are typically easier to deal with. So this would still have to be an EI than it would be to deal with the UG rules. Sometimes that'll be more useful than other times, but that's just one helpful idea. Let me actually mention just one more thing before going on, because I know this is a very common question people have. Let's say you had, let's just go back to our argument. Yeah, everybody's a P, and every P is a Q. Notice this sentence is very different, right? That sentence is very different than saying everybody, if everybody's a P, then everybody's a Q, right? Like let's just to make sure we're all on the same page. This is saying just anybody, if you're a P, then you're a Q. This is saying here the conditional is the main operator, and this is saying if it's the case that everybody says yes to being a P, then it's the case that everybody says yes to being a Q. And so those are just importantly different sentences, right? This one could say all dogs are mammals. This one says if everybody's a dog, then everybody's a mammal. So in that sense, that's true. That, well, I suppose it's true, but I mean, it's only true because that's false and that's false, right? This is true because oftentimes this is true and oftentimes this is true. But anyway, I'm not going to get into that much. The point is there, really, you have to watch out for your main operators. Really what I wanted to get to here was so we have those two premises again, and then we're trying to get to our conclusion. Everybody is a Q. So, I mean, honestly, we're actually proving that other statement that we were talking about, but it's still an importantly different statement, right? We can prove this statement from those premises. But anyway, well, so I'm not going to get into it. This was our old conclusion. I just want to point out, let's just change this variable. Let's just change it to y and change this to y. And even like, we can even change, well, so I'll just do it just with that change right now, just to show you. We're just going to do the same exact thing as before. Nothing is actually different here, except, so I guess I'm doing a generalization or universal there, but I mean, nothing is different here based on just the variable change, right? We're still going to do, right, I'm not using E's anymore, or existentials, but that's fine. So if everybody's a P, you know what, just for the sake of lack of confusion, I'm just going to go back to what I think we had earlier, which is that one of these was actually, we were actually saying it was just, but I am going to change that variable just to show you it makes absolutely no difference, right? Because it's still just, this sentence is saying somebody's a P, anybody who is a P is a Q, that means somebody is a Q, right? That's all this argument is saying. It doesn't matter if I used X to do it or if I used Y to do it, right? And it's not going to make any difference in the proof either, because all I'm going to do is still just going to be my EI first, PA, EI, 1. And then I'm going to do my UI, PA to QA, right? EI before UI. And then I'm going to do my modus ponens. and then I'm going to do my generalization. Except it's just this time I'm just going to pay attention. What does the conclusion ask me? Which variable does it just happen to ask me for? And here it just happened to ask me to put it in terms of y's. But again, nothing hangs on which variable we choose, right? So we're just fine choosing this variable, choosing this variable, even though we started off with x's, right? We could have even started off with, just go ahead and change these. These could have all been z's, right? As long as they're variables. For everybody out there, if you're a p, then you're a q. This is why I say when you're translating these sentences, it's helpful to try to not say the variable, just say things. Because the point is the variable is just completely unimportant. It's just so that if there's more objects going on in here, you know which ones the quantifier is actually talking about. That's the only reason we even have the variable. It's just to tell us, okay, this group of people you've introduced, what are you actually trying to say about them? But it can change each and every line. You can, here we use z to talk about everybody, but later on you could use x to talk about everybody. It really just does not matter. So for instance, just with the changes I just made there, just with that, this, I don't actually even have to change the proof at all. This is still just going to be a UI on 2. It's still just going to be, oh, well, I'm going from quantified statement, throwing away the quantifier, and swapping that variable out for a particular constant. So absolutely nothing changes, even though I'm using different variables in here. Right. Okay. Now, just just because of how these programs are written, typically when you have a proof checker or something like that, or just because of how modus ponens works, if you have something like, and this sort of thing is more trivial. So if you, I mean, maybe I should have mentioned this earlier. If you want to fast forward to the last rule, just to get it, that'd be good. But these are valuable tips, I think. Right. So this isn't going to be a very common thing that pops up, but it could happen, and I just want to make sure you've been exposed to it at least once and how to. Don't be alarmed when you see this sort of thing. Like if you have it that if you have a sentence just as simple as, let's say, if Aristotle's a P, then everybody is a Q. I don't know. Right, that'd be weird to be true. There's Aristotle being a parrot means that everybody is something or other. Right, weird sentence, but we can formalize any sentence as long as it actually makes some sort of sentence. Anyway, or hold on a second. I'd rather flip this around. Let's say if everybody is a Q, then Aristotle is a P, or whoever A is. And then let's say, so that's premise 1, and let's say premise 2 is that for all y, qy. Right? And then down here, we just want to prove that Aristotle is in fact a P. So this should be really, really obvious, or at least, I mean, it seems like that. This is just saying, if we read this in English, if everybody is a Q, if we can check off that everybody is in fact a Q, then we know Aristotle's a P. And then premise 2 is telling us, in fact, yes, look, everybody is a Q. You can go down that list of everybody in our domain. Oops. We can go down the list of everybody in our domain, and everybody's going to say yes to Q. But what's the problem here? The problem is that the variables don't actually match up. And remember, modus ponens, all of these rules are so particular. They need these things to match up exactly, right? So when we're doing modus ponens and we say, oh, I need the left, and then I'll be able to get myself the right. Well, yeah, that's my right down there, right? So all I want is to get to this guy right here. If I can get that guy right there, then I get my right side. So we can go through and we can scan. Do I have this guy? No, we do not have that guy. These are in fact these just simply have different characters, right? So I mean, it might feel annoying, but I mean, it's just the fact of the matter is that is not the same sentence as that. I mean, they mean the same thing, but us being able to understand that they mean the same thing, that's us just being good logicians and understanding how these things work. You have to prove that they mean the same thing, right? Like, I mean, I could say just as far as the whole argument goes, like, oh, I can just see it, right? Like, that's all you're telling me when you tell me that these mean the same thing. You're just telling me you can just see it. And so what we need to do is we need to make that absolutely explicit. So the idea here is all that we need to do. I mean, it feels annoying and just like just a bit extra, but the idea here is we're just first going to do a UG or UI, excuse me, and get an arbitrary constant from 2. And then right away, I'm just going to lose that arbitrary constant in favor of my preferred variable. Right, so that's just going to be a UG. And UG is definitely, it's a restricted rule, so I need to look down at my restrictions and make sure I'm not violating it. And so I need to make sure first, did I get that, like the A that I'm losing, that's what I care about. Did that come from, oops, it did in fact. Did that come from any premise? And here it did. So actually, I shouldn't have chosen A in this case. I'd rather not choose A because I don't need this. In order to do the modus ponens at the end of the day, I don't need this left side to have anything to do with A. In fact, I don't want it to have to do with A. I want it to be this big universal sentence. So really, I want to choose a brand new sentence, a brand new constant, even though this is a UI, even though there wasn't a violation when I did this line, it led to a violation down here. So the idea is I need to make sure I just grab a completely new constant. That actually isn't even the main point of what I was trying to show you here. The main point I was trying to show you is just that you need to watch out for, yeah, they mean the same thing, but you need to prove it. And we just ran into an extra complication in proving it, that we happen to have a constant already in the sentence, and that was really just a complete accident. And so the way we watched out for that was we just decided, okay, that's fine, but all I'm trying to do is just this UI UG. I'm just ducking in and out, basically. I'm just trying to swap my variables out for my universal. And when I do that, I'm just going to grab a completely new constant, right? So now that I have B, now I'm able to do this UG successfully and without any sort of violation. So now I do have the left side. And so now I'm able to get my right side on the very next line. So that would be 5 right there. And so that would be modus ponens. Right, and we can do a modus ponens now, right, because the main operator is the conditional. We have that quantifier is completely restricted over here. Okay. Right, so this is going to be a UG just from 3. So the moral of this story, aside from the brief side plot of make sure anytime you're doing this, you're using a brand new constant, is the following. So when you see that you have 2 universal sentences and you can tell that they are in fact exactly the same, all that you need to do is a quick UI and then a UG, right? Duck in and out of using just a brand new constant, and just make sure that that constant isn't anything from above. Even though the UI wouldn't care, the UG that comes to follow does care a lot. So make sure you just grab a completely new constant when this sort of thing happens. Right. Okay. Okay, I know I keep mentioning that we're going to move on to that last rule, but there's a lot of just little things that it's good that we're going over now, because it's just good that we're being able to see these all together. But one other thing you might think of doing in this case, like if you hit this and you say, oh, wait, I remember when I saw this in the video or whatever, And all I need to do is do a UG, or a UI and then a UG. And so you might jump in here and you might try to say, okay, so that just means I'm going to do a UI for Q. Well, oh no, I also remember I need to use B. I didn't want to use A for PA. Right. And then I guess I'll just do a QB and then I'll get a PA. Well, that's no good, right? Because this, you're trying to do a UI here, right? We're trying to lose that quantifier, but you cannot lose this quantifier. The only way you can ever do an instantiation rule is if this quantifier is the main operator on the sentence. So that's very important, and I should have made a bigger deal about this throughout. But the idea here is we can't do a UI on this unless there was like parentheses around the whole thing. That's the only way we can do a UI. So that's why we were able to do it to 2, because the quantifier is looking at the entire thing. But we can't do a UI if the quantifier is just looking at a part of the thing. Similarly, we can't do a generalization rule if the quantifier, or just to a part of it. We would, anytime you go from a sentence, like if you had PA QA, you can't go from that to, you can't just have that and then go immediately to just, so if there is an X, so it's that PX, then QA, right? The idea is you would need to take that entire sentence, wrap that entire sentence up, and then throw away the constants. So throw away a single constant, just make sure you're throwing away that constant every time it appears. And then you can add the quantifier to the sentence as a whole. But that's the only way that you can do these instance and generalization rules. So just the last thing on that is a lot of the times I'll see something for like one of these proofs. So a lot of the times I'll see something that looks like this, where you have for all X, if X is a P, then QX. And then PA, and then they're trying to get to QA down here, right? So if you're still like just grasping this, now's a good time maybe to pause and think about how you would actually prove this, because I'm going to show you what not to do, right? So a common mistake to do here is, oh, this one has the quantifier, but this one doesn't. So let me try to add the quantifier on. And then I can do a modus ponens and I can get the QX. And then I can just do an instance rule and I can get the QA, right? So the idea was I'm going to go from this one and add the quantifier. And now I can take this one and do a modus ponens. And then I can do that. But that doesn't work at all, right? And because the idea here is, again, well, there's a lot of things wrong with that. But mainly, or maybe not a lot, but maybe this one extremely important thing, you cannot do a modus ponens on this. This is not a conditional sentence. This is not an if left, then right? Because the point is, this is a universal sentence. The left and right is completely contained in these parentheses. The universal is not on the left side of the conditional. It's wrapping the entire conditional up, right? That's very important to see. The universal is not on the left side of the conditional here. It's around the conditional. Okay, so you cannot do a modus ponens there. Even if you already had this line, this for all X, PX. I mean, again, the point is, this is not a conditional. The left side of it is not just for all X, PX. You cannot do, there's no conditional to even match up here for modus ponens. You need to turn this into a conditional by throwing away that quantifier. That's the only way we're going to be able to do it. So it does us no good to just start adding quantifiers. That's why it's very valuable to just, when you're doing these things, start off by thinking, tear away the quantifiers. Don't just try to match stuff up arbitrarily by adding quantifiers randomly. Start off by trying to tear away these quantifiers and later, if you need to, you can add them on. Okay. All right. That's basically it for these 4 rules and the handful of very common complications that we can get from them. I'm going to go ahead and keep this because I think it's good to just have with it, really. Okay. Just because I wasn't able to take all of that anywhere. So I think that's just kind of good for us to have always in the back of our minds while we're doing these quantifier rules. Okay, so the idea here with our final rule, this is actually something that shouldn't be too hard for us to get through because we looked at it a little bit in the translation section, and if you understand just kind of what these sentences mean, then this should be really simple. And this is quantifier negation, so QN. So the idea behind quantifier negation is, well, if you have a sentence like this, for all x, fx, right? This is saying everybody speaks French, or whatever f is. So the idea here is, if we negate that sentence, well, we're just saying that some universal sentence is false. So we're just saying, again, a negation is just flipping the truth value. So if the truth value of the universal sentence is that you can look down the entire list and everybody is going to report T to your question, R, U, and F. Negating that is just saying that, no, you're gonna fail. And that doesn't mean I'm going to fail every time, right? That's way too strong. You're wrong to say that universal sentence just in case one guy fails, right? Like, let's think about that. Let's say you were going down the entire list and you asked, okay, yep, true, true, true. Oh, and there's a false. Then go ask yourself the question, is it true that everybody speaks French? Well, this guy said no. This guy said false. This guy, right? Cross, not at. No, I don't speak French. So the idea is it's not true that everybody speaks French, right? So really, so for all these guys, yeah, I speak French. I speak French. I speak French. This guy, right? Whatever, whoever this guy is, does not speak French. Right? So the idea here is we can negate the universal sentence just as long as somebody says no. And that is actually just going to be the same exact thing as saying you can find someone on that list that says no to speaking French. And that is quantifier negation. It's one form of it. Right? So the idea here is you're saying if it's not the case that everybody does this thing, then that means you can find somebody that doesn't do it, right? If it's not the case that everybody is a millionaire, then somebody is not a millionaire, right? If it's not the case that everybody went to the party, then you can find somebody that's not at the party, okay? And I mean, again, this should make sense just in terms of these remember we talked a little bit in the translations portion that a universal sentence, fx, this is just saying fa and fb and fc, right? This is just a super long version of saying that sentence, right? Or excuse me, it's a shortcut. It's of saying this super long sentence, right? To say everybody is an X is just making this long conjunction of saying first guy on my list is an F, or is an F. Second guy on my list is an F. Third guy on my list is an F. And we're just going through the entire list and just saying and. And remember, the only way for the and to be true is if each and every part of this is going to be true. So if you ever go ahead and throw that tilde in, well, then you can take that entire sentence and throw a tilde on that too. And then use De Morgan's. So what happens when you put a De Morgan's when put a tilde on the outside of that and? You get something that looks like this. When you push it inside, it's going to attach to every guy, and we're going to flip all the ands to ors, right? And that's going to be true for the entire line. And again, remember, a long list of ors, that's just what it means to say that, oh, well, I don't know who does it, but somebody does it. I don't know. Maybe either A is not an F, or B is not an F, or C is not an F, or D is doing it, or Z. But the idea is we're just saying, somebody's not doing it, right? And so that's exactly what it means to say there exists, right? The ors, long sequences of ors, that's exactly just, we have a shorthand for that. That's the existential quantifier. And so we existentially quantify this statement that it's not the case, right? So this should show you, right? We talked about this before, I've already mentioned, but quantifier negation is really just De Morgan's, right? Because all the quantifier is just a shorthand for a long list of a conjunction or of a disjunction. And so all that we're doing with quantifier negation is pushing that negation inside and out. Okay, so just like with De Morgan's, just like with regular De Morgan's, there's two forms that this can take, right? You can start with the negation on the outside of the and, or you can, and then push it so that you have a bunch of ors, or you can start with it the other way, right? So we could say there is someone such that he doesn't speak French. Oops, I just grabbed the same exact sentence, right? So we don't want the same exact sentence. We want the opposite. We want to say it's not the case that there is someone that speaks French. And we want to understand this now. So what does this mean? So remember, just the existential sentence alone means you can go down, you're going to be able to go down this list, and you're going to be able to find me at least one person that says true, right? So so I'm happy just as long as somebody says yes to me. So if you negate that, if you're telling me I'm wrong, that means absolutely nobody said yes to you, right? Everybody said no to being an F. And so that's exactly the same as saying for everybody out there, they all said no to being an F, right? And so that's exactly the same as if we had this long series of disjunctions, right? That is just going to be the exact same thing as saying, oh, well, then it's not the case that A, and it's not the case that B is an F, and ... Right. So again, this is just the other form of De Morgan's when it's the or on the inside of parentheses and you push the tilde into that one. And again, once you get to the ands, now that's just a universal. You're just saying, oh, you're just going to make a list for everybody out there and tell me everybody out there is not an F? Let's just use the shorthand. Everybody is not an F. Right. So this quantifier negation is really just De Morgan's. And in that sense, it's actually just as vital as De Morgan's, right? You're not going to be able to do propositional logic proofs very easily, at least, without De Morgan's. You can use the other rules to prove De Morgan's, so you actually aren't going to tear it, but it's vital to doing them with any sort of sanity in any sort of reasonable time frame. If you don't know De Morgan's, you're going to be spending hours doing the simplest things. And it's the same thing for quantifier negation. You definitely want to be very comfortable with quantifier negation. And I mean, it shouldn't be too hard, right? I mean, the only thing that's happening here is just you have a tilde next to a quantifier, and you can push it to the other side. And when you do that, you just flip which quantifier you're using, right? If the tilde is on the right, then you push it to the other side. And so if you started off with a universal, when you pushed it to the other side, you ended up with an existential. So this really shouldn't be hard at all how to do a quantifier negation. All we're doing is just pushing the order of, is it negation quantifier or quantifier negation? And if you want to swap the order they appear in, that's totally fine. You can always swap the order. No matter what order they started in, no matter what quantifier they started with, you can swap it and just flip which quantifier you have. It really, I mean, it couldn't be more simple. Okay, so that's quantifier negation. So let's go ahead and, I know I said I wanted to do more examples. Hopefully the examples we did while looking at just these rules helped out a good amount, because I don't want to make this video too long, and I can't make this video too long. But let's go ahead and try to figure out how we might use these rules together a little bit. So let's say our first premise is, let me use a different color. Let's say our first premise is it's not the case that somebody is P and a Q. All right. So then and then premise 2, I'll go ahead and say that B, just Billy, just grabbing a name at random. But we're just going to name one of the guys on our list is going to be list. And one of the guys is Billy, and he's saying, yes, I am, in fact, a P. I'm a parrot or whatever. And so what we want to do is we want to conclude that that means, Billy, you must not be a Q. Okay. Right, so let's go ahead and see how these, see how complicated or how quickly we can get through this one. And then we'll decide on what to do next. Okay, so the idea here is, let's first just think through this argument just in English. So the first sentence is saying it's not the case that there exists something that's a P that's simultaneously a P and a Q. Oops, this was supposed to be Billy. It's just a messy B. And then premise 2 is saying, okay, well, Billy is a P though. And we're supposed to conclude from this that that must mean Billy is not a Q. Right? If you say something like there does not exist an honest lawyer, and then you learn Billy is a lawyer, then you can conclude from that, well, then that must mean Billy isn't honest. Right? And again, just a note on the logic of it, this is just if you assume that those premises are true, we can conclude that, right? And so maybe you think Billy is honest and he's a lawyer, and so that would teach you to reject that premise. But again, now we're getting into the philosophy of it all. The idea here is if we assume that premise 1 is right, we assume, right, so we're never going to be rejecting premises in this class. That's for philosophy and just, I mean, your own thinking when you're just making reasonable arguments about day-to-day life and religion and morality and science and whatever. But let's set that aside. Right, so the idea here is we're assuming that there does not exist something that's a P and a Q. Billy, in fact, is a P, and we're trying to conclude then that he's not going to be a Q. And so one way we could do this is, well, you could say, well, suppose he was a Q, and then we could try to figure out what contradiction we have. So actually, this is going to go really smoothly. Well, one thing we could have, well, so now when we supposed that Billy, oops, let's formalize this. I'll go ahead and do this proof in a couple of different ways. Because this isn't typically the way that that we might approach this, but I'm just going to go ahead and give you one way that these proofs can work. So one way we can do this is just, well, suppose Billy is a Q, right? So let's just assume. And the idea is I'm going for a contradiction down here. And if I can get that contradiction, then I get this, right? So I'm just starting off in this way, just to show you that our old school proof methods are still completely open to us. And so this is just going to be RAA, because we're trying to end in a contradiction. And then we're going to return and say, oh, then the moral of the story is whatever you assumed was wrong. And that's exactly what an RAA does. So what we can do here is we can say, okay, well, you're telling me Bill is both a lawyer and he's honest. So that means somebody is both a lawyer and honest, right? So we can look just back at our rules. Existential generalization is a green box, so we're totally safe in doing this. Don't have to check anything. And then look at what we have. we have a contradiction, right? So what's our contradiction? So remember, a contradiction is just something of the form stuff and not stuff. And so we have not stuff up there and stuff down here, right? So this is just to point out, like, these, it can, the RAA still works just the same. And the sentences that you contradict can be quantified sentences. That's totally fine, right? So we can end this proof pretty quickly just by saying, okay, then on one line you said there is somebody that is a P and a Q. And then on another line you said it's not the case that there's somebody that's a P and a Q. So you've contradicted yourself. So, I mean, I've omitted the lines here, and I really shouldn't do that this early on doing proofs. So we're assuming on line 3, we're conjoining on line 4 with 2, 3, right? Then we're doing a existential generalization, right? And that's safe on line 4. And then we're doing a conjunction or a conjoining lines 1 and 5. And then once we have that contradiction, then we can just step away and we say, okay, lines 3 through 6 via RAA give me my conclusion. Okay, so oftentimes the proofs aren't really going to work so nicely. Here we actually didn't have to tear off any conclusions at all. Actually, we didn't really have to do much of any work with the quantifiers. We had to do one generalization. So this proof and the method in which I did it isn't, I mean, in some ways maybe it's not the best to start with because it's not exemplifying our 3-stage method. But that, if nothing else, the point of me showing you that way of doing it is just that to give you a little bit of experience in seeing an RAA with, right, of seeing us do an RAA with quantifiers involved, and that it's still okay. Okay, well, let's do it maybe more of a natural way, or more of a way that that I would recommend trying to approach every proof. Still, the first thing actually I always do is still check, is my conclusion a conditional? And it's not, so cool, I don't have to worry. And so now I'm just going to come up and I'm just going to say, all right, let's try to work to try to do stage 1, right? So we're going to try to do stage 1 first. And in stage 1, we're trying to instantiate, right? So we're trying to take off quantifiers. So premise 2 doesn't have any quantifiers, so I'm not even going to worry about that one. Premise 1, though, does. And so can we take off that quantifier? Well, the answer is no, right? So we can't take off that quantifier because it's not the main operator. This whole sentence is really just a negated sentence. This is just one big, it's not the case that blah, right? This is why it's so important to be able to pick out what's the main operator in these sentences. So if we know it's not the case that blah, so the idea is this is one perfect place where QN comes in handy. So QN is oftentimes what you're going to want to do first when you have a quantifier and a negation and they have this order. So if you have it like that or you have it like that, you just have that tilde on the outside of the quantifier that's making it so the quantifier is not the main operator. So either of these forms, whoops, we would have wanted to do QN too. So let's go ahead and do that here. So we'll say for everybody out there, it's not the case that you're a P and you're a Q. And so now I am in perfect position to tear off my quantifier. So I'm going to check to see, do I have to do any existential instantiations or anything like that? Because I'm trying to remember, you always do the EIs before the UIs, but I don't need to do that, right? The only other premise out there is 2. We just got this thing from 1. I mean, the whole point is we couldn't have done an instance rule to 1. That's why we gave ourselves this new line on 3. Right, that's 3. And so now we can do a universal instantiation. So we're going to throw away that quantifier, and we're just going to get px, except we're also going to throw away that variable, right? So we're going to keep, we're going to keep the sentence, except throw away the quantifier and replace the variable with a single constant. So we're going to keep the sentence exactly the same, except we're throwing away that variable for the single constant. And now the question is, what do I want to put in place of that constant? It has to be just a single letter both times, because this was x both times. So, and so the idea here is, generally speaking, you want to match, right? We want to match our endings, right? That's the only way we're going to be able to do our logic in the next phase, right? So we're looking forward to the next phase when we're able to do, right, our prop logic, right? So that's why when I do my universal instantiation here, so remember, universal instantiation is in the green box. It's completely safe, so I'm allowed to do it with whatever constant I want. It's okay that it's using an old constant. And the reason why I'm using an old constant is because I want to be able to do, I want them to be able to do things like DS or modus ponens or things. And the only way they do that is if they agree on it. At one point, we had to worry about, like, the reason why we chose a different constant earlier in an example, because I'm sure there's some confusion about that, is because we were trying to do a UG later, and UG needed to make sure the constant we had wasn't from a premise. So it was just because we were doing a UG that we didn't want to make them the same. But in most cases, we do want to make these constant match up, because that means in this next section, we're going to be able to do, so we're going to start it off with the De Morgan's. So let me finish up by, let me put in the rules here. So we did just a QN right there, right, to line 1. And then we did a UI to line 3. And now the idea is the next thing we're going to do is just a De Morgan's, right? Anytime you have that negation sitting on the outside of an or an and or an or, it's best just to push it in. And now you should be able to notice, like, oh, cool, I've got a near miss. Like, this is either, you could either treat this as a DS, that you just need to put 2 more negations on that. Or what I like to do, I think it's very helpful if you start thinking of ors and implications as interchangeable. Because, right, and that's via MI. So being familiar with the MI rule it can be very useful. So this isn't A, this is a B. So MI says if you have an or with the left side with a negation, switch the order to an arrow, and then drop the negation on the left side. Right. So that's just MI. Again, you could have just let me not leave these here. You could have just taken 2, done a double negation on your next line, 2, and then done a DS with 6. That would have worked just fine too. But so this would be, I'm losing track of my numbers now, so let me renumber these. Okay, so I'm just going to go to black to keep it simple. So this would be 3, 4, 5, and 6. And then in 7, we'll talk about that in a second. So first we did a QN, right, to 1. And the whole point of doing a QN to 1 was just because we wanted our quantifier on the outside. And then we did a UI to 3. And that's why we put our quantifier on the outside. So now we can instantiate. And the point was, right, that was our target in phase 1, in stage 1. We're trying to tear off our quantifiers. So we put it on the outside. That lets us tear it off. And now that we've teared it off, now we can enter stage 2. And the point of stage 2 is to start doing old school logic, things like De Morgan's. Right, so we're doing De Morgan's on 4. right? That's still our conclusion. And then the way I chose to go about it was just doing an MI on 5, right? Which is just utilizing the fact that ors and arrows are interchangeable just as long as you throw an extra tilde on that left side. I know that's one of the lesser of the intuitive rules, at least when you're not quite used to it yet. But just I refer you to the video where we go over the logical or the propositional logical inference rules. And just find the section that goes over material implication. It's easiest to see, right? We look at it with a truth table, and that's the easiest place to see it. But anyway, let's go ahead and finish this off. So now that we have PB, and if PB is true, then not QB, then we get not QB, right? And this is still in the propositional logic section. And so here we just needed the modus ponens with 6 and 2. Oftentimes, I mean, maybe I just made this conclusion a little too simple. Oftentimes the conclusion will just be more like this or something, right? And so once you got there, you would just do something like an existential generalization. So in this case, we really only had 2 phases. You just tore off quantifiers and did some old school logic. Oftentimes, you'll also have to add on a logic or add on something. So actually, let's go ahead and let's pretend I had more foresight, and let's pretend that actually that our conclusion was this all along. I mean, it doesn't matter now. Like, if you want, just erase everything we did and then act like we just redid it right now. Right. So the argument is still valid. The argument is still valid. We're saying, okay, we're starting off saying it's not the case that somebody is both a lawyer and honest. Barry is a lawyer, though. So that means it's not the case that everybody is honest, is supposed to be our conclusion. And that should make sense, right? Or we should be able to accept that based on these premises, right? So if it's not the case that someone is an honest lawyer and Barry is a lawyer, well, then we know he's not going to be honest, which means that we know it's not the case that everybody will be honest, right? We know somebody will tell us no on this big list. In fact, it's Barry. Okay, so the idea here is we would do exactly the same thing we had been doing, where we get not QB right there, right? And then, so I'll continue it all on right to our left right here. And then the idea is the way this would go is now you'd be in add quantifiers, right? We're in this section now. Right. So now that we're in the add quantifier section, we've proven that Billy is, or Barry or whoever is not Q, is not honest, or whatever we're going to say that it means. And so that means we can do our generalization rule. Now let's think about this. So should we add on a universal operator or an existential operator or quantifier? So if we just said that somebody, well, let's think about it. So if we tried to do a generalization rule here, let's first think about where the quantifier goes. Well, the idea is we have our sentence, not QB, and when we're doing a generalization rule, we're throwing away the constant, and we're replacing it with a variable, right? But where does the quantifier go? Does the quantifier go right here? Or does the quantifier go over here? Right? And also, I mean, it's not a given that we're even going to use the universal here. Right? So, but the question is, where does the quantifier go? And the idea is, it always goes on just the outside. We're always just going to wrap the whole sentence together, in a sense, and just put it on the outside. Again, I'm just choosing a quantifier at random at this point. And right, so that's going to be the way it goes. And with a tilde, right, we don't need to wrap this in parentheses. It's a given that this is already has kind of implicit parentheses around it. So now the idea is the quantifier is going to go right there, because that's the only way generalization rules can work. You always add it to the furthest thing to the outside and just make sure the entire sentence is going to be affected by it. So if there was like this and stuff, we would make sure that we wrapped it in parentheses. Okay. So now we just need to figure out which quantifier we add on. If we tried to add on the universal, well, think about what we would have tried to do next. Like, aside from whether or not you're probably gonna be violating restrictions here, actually, because you're trying to lose a constant that came from a premise and you can't do that. But let's say, like, let's even ignore that for a second. The reason why this wouldn't be good is because right after you added on that quantifier, well, that's not in the right order, right? You would want to switch that order. And the only thing that lets you switch the order is De Morgan's, and then you ended up with this sentence. And that's not what you want. So really what you wanted here, so because actually the quantifier is not, in the conclusion, the quantifier is not on the outside, you want to introduce the opposite quantifier. So when you put it on the back on the inside, what the conclusion wants, it turns into the quantifier that you want. So again, I mean, really, we weren't even going to be able to do the universal there because that would have violated. But the idea is we wouldn't even wanted the universal there because it wouldn't have given us the right answer at the end of the day. So the idea is we're going to generalize existentially, right? And that's a safe rule that we can always do. And then right after that, we can do the QN. And then we finally have what we're looking for, our conclusion. So this one, right, was just existential generalization on 7. And then 9 was QN. So this gives you an example of a few things that, I mean, some of which we've already talked about. But otherwise, I mean, so sometimes you're going to add on the quantifier and you need to do a little bit extra. Like you need to shift where that quantifier occurs. So this last stage is like kind of quantifier cleanup. You're adding some back on. You're maybe doing some QNs and stuff like that. But generally, it's after you've done the main bulk of your logical work. Okay, so that's basically it. It's basically it for just the basics, at least, of these proofs. Let me show you one other example, or at least one other example, just real quick. That we touched a little bit on this sort of thing, but I mean, it's just important for us to look at because of how common it is. Okay, so what if we wanted, I'm going to try to not take too long, so I'm going to try to not like break it up with all the colors and everything. But like, what if we wanted to get to the conclusion, therefore, every P is a Q, right? I think that's too small to write it. I'm going to try to write this a little cleaner because oftentimes we'll have conclusions that are universals. And oftentimes it'll be like a universal conditional. So to be clear, like if my conclusion was really, and so I'm going to put in some premises real quick that we'll use to get to that conclusion, but in just a second. So if my conclusion was something like this, right, now the conditional is the main operator. So now, like if that was the case, I would have just set it up as an old school CP. Really, so there wouldn't have really been any difference than just doing an old school CP. Right, that's if this was, I mean, that should make sense. The conditional is the main operator, the fact that there's a quantifier on the left side and a quantifier on the right, that really just doesn't make a difference, right? We're still just going to follow the same rubric of putting the left side up top and the right side on bottom and the entire thing on the very bottom. So if that's our conclusion, and the conditionals are just on either side, or right, the quantifiers are on either side of the conditional, and they're not the main operator, but the conditional is the main operator, then we're going to do what we always do when the conditional is the main operator, and we're just going to do a CP. On the other hand, if we have a conclusion like this, we can't just say, oh, assume everybody is an X there, and then I'll get you to everybody being a Q down here. And then, because if you did that subproof, well, all you're showing me is that if everybody's an X, then everybody's a Q, right? You're just taking this left side and you're showing me it leads you to the right side, right? But if I'll throw at least this down in color. You're just taking that and showing that, right, leads to that, right? So that's how a CP works. But recognize that this sentence down here is not the same as this sentence right there, right? So doing a CP on this problem wouldn't help at all. At least not that style of CP. Oops, actually no, I have to do this. Okay, but what we can do, so let me go ahead and throw some premises in here to make this a little bit more worthwhile. So I'm just going to go ahead and say it's not the case that there exists a P and a Q. Okay, so this will be a simple argument that we could prove it actually in a lot of easier ways, but like many of these examples, the point of this isn't to find the easiest way to prove it, it's just to show you a couple of techniques or things that pop up. So a lot of the times, so yeah, I don't want to show you the easiest way, the shortcut, if you will, to prove this. I want to show you how you should be approaching these proofs when you see them, even if there is technically an easier way. If you're clever enough to find those, by all means, go for it. But this is all about how you should just generally approach them. So the idea here is, sure, this proposition, this conclusion isn't a true to form conditional, but it is a universal conditional. Like it is the conditional. It's not totally irrelevant. The idea is, right, this line here is just saying that for everybody in our domain, they're all going to say yes to this, right? That each person is going to be like, yeah. For me, it's true that if I was a P, then I'm a B. And some of them, it's going to be true because they, in fact, are Ps and they are Qs. Some of them, they're not going to be Ps, but they're not going to be Qs. So but the conditional is still true. Some of them might not be Ps, but they're still Qs. And right, just because of how the conditional works, we're still going to call it true, not false. Something like that. True. Sorry about that. But the point is, if I'm trying to conclude that everybody is going to say yes to this conditional, then really the way we can talk about this is just, let's prove it for some generic individual. And we talked about this a little bit when we were doing UG. But I'm just going to choose a completely new name that hasn't been used anywhere else in the proof yet. And in this case, there hasn't been any names used in the proof yet, so I can choose just any name I want. And I'm going to show for him just this completely generic individual that if he was a P, then he would be a Q. Wait, sorry. So I think I messed up actually here with the. So let me change this premise just a tad, actually. My apologies. So this premise really should be, yeah, I messed up here. So this is actually not a valid argument as it stands right there. I need to put in a tilde. right? And so if you were a little worried about this as I was going through and you had a question on it, you were right to. We're trying to say from the premise that it's not the case that you can find somebody that's a P but not a Q, right? That's the premise. It's not the case you can find somebody that's a P but not a Q. And from there, we're trying to deduce that everybody that is a P must be a Q. For everybody out there, if you're a P, then you're a Q. Right? So if it's not the case that there are any P's that aren't Q's, then everybody that is a P must be a Q. Okay. So again, so now we would be able to prove it with other logic methods. Earlier we couldn't prove it because it just wasn't valid. But now we can actually get started. So. Right. Okay. So the idea here is we're just going to show that this is true for some generic individual. And if we can show it's true for some generic individual, then we've shown that, right, at least for this individual, generically, I'll keep throwing that in there, that conditional holds, right? And so this is just actually this is just a vanilla CP. It's really not even anything special about that. Right? This is just saying, if you start a subproof with the left and you can get it to the, or if you can start a subproof with something and you can get it to another thing, then you've proven the conditional of this form, right? And now, so the idea is once I've proven the conditional of that form, now on the very next line, well, because this A didn't come from any EI and it didn't come from any premise or anything like that, now I can generalize on it. And so now I can actually I can throw away that A in favor of the variable that the conclusion wants to be looking at. So the last line of this is actually going to be just a UG on whatever line this turns out to be. Right, so if that's line number, it's just going to be a UG on number, right? And then this is going to be a CP on 2 through number -1. Right, okay. So the idea here is when you see that you have this form of a sentence, you should notice, yes, that it's not a true to form conditional. So you can't do just a straightforward CP and then immediately end at your conclusion, but you can do a slightly altered CP that gets you to a conditional that's really close. So I mean, it's still like every CP is just going to be the same thing. It's just going to be a left to the right, and then you get a conclusion that's a conditional. It's just that now that conditional that you get isn't exactly what your conclusion is, right? The conclusion that you get out of the moral of the story for this subproof isn't exactly the conclusion that you're looking for. But it's okay because it's just one step away. So again, let me just try to reiterate that just one more time. The point is, when you have a conclusion that's some sort of universal conditional, so this is a universal conditional. So when you have an A statement as your conclusion, just still set up the CP, but just do it with an arbitrary constant. And you're still gonna, like, the CP ends the same way just by putting the top together with the bottom. And then just remember to do a UG right afterwards, and that's what will actually give you your conclusion. So now the only work we have to do is, how do I get from the PA to the QA? Once I do that, I know PA really showed me that if PA is true, then QA has to be true. And then I can generalize. Because there was nothing special about A, I know that because it's going to be true for everybody, that if you're a P, then you're going to be a Q. Right? So I'm trying to show that for everybody out there, if you're a P, then you're a Q. So I'm just grabbing a generic name and showing, well, just take A. If he's a P, then he's going to be a Q. And so then I've shown that if A was a P, then A was a Q. And the idea is I could have just gone and done that for absolutely everybody. And if I can do that for absolutely everybody, and I certainly can, because there's nothing special about me doing it for A, then, I mean, it's just a bunch of ands, right? I can do it for this, and I can do it for that, and that's how we prove the universal. Right, but we only, so we don't actually need to do it for each and every constant. We just do it for the one constant, and because this is a generic constant, we can do the UG, right? So this is how the proof will actually look right here. Okay. So now our only job is to try to fill in these blanks. So we can go ahead and if we want to work with this first line at all, we need to tear off this quantifier. And the only way we can tear off the quantifier is if it's the main operator. So we'll go ahead and do that. And now we can instantiate it. We can tear off that quantifier. Oops, I don't, but we're throwing away the variable, right? So we want to think, what do I want to, because I'm tearing away the quantifier and it's a universal, it's a UI that I'm doing right here, right? So this was a QN on 1. This was an assume. So I'm doing a UI. UI doesn't care what's going on. Like it's okay getting an old constant. So I want to use A because next I want to be able to make the A or make the PA and I want to be able to make line 2 and line 4 talk to each other in a sense, right? And if I chose a brand new constant, I wouldn't be able to. So I'm going to use this A again. UI doesn't care how many times A has been used before. And now I can do my De Morgans. Right, so if I'm pushing this tilde through, I'm taking this and changing it to an or, and then I'm putting a tilde on both sides. So the PA turns into not PA, and the not QA turns into not QA, because you're adding another tilde to it, right? You're just taking this tilde and adding it to both sides. So if you already had one, you just get another one. Okay, but now the idea is we already know PA is true, and this is saying either PA is false or you get this right side. And remember this right side, well, we can just go ahead and do a, go ahead and grab make that smaller down there. Sorry for the sloppiness. All right, so but the idea is we're still trying to get down to this QA at the end of the day. So let me go ahead and erase the color coding because once you have the CP set, you can kind of forget about what the structure was. As long as you did it right, you don't have to worry about what the structure was. You did it right. So as soon as you have that color coding set, you can be comfortable and confident. I can erase that, or I can, right? We can stop thinking about that. And now I just want to again use the fact that I have PA. I have either PA is false, or I get all this. So right now I see that I have a double tilde, and now I can use an equivalence rule. Now because remember I can use equivalence rules on just parts of the sentence, right? So implication rules like modus ponens and all of these rules that we've been using, we had to make sure what we were looking at the main operator. But things like De Morgans, we can actually just copy down that sentence just the same and just substitute just the part we don't want. So I don't like that part, and I'm going to substitute it with just QA. And what lets me do that? DN lets me do that. Right, so double negation lets me just take a part of a sentence that has 2 tildes and just throw those 2 tildes away. So I'm doing a DN to 5 here. And now, notice that's a perfect, again, MI is such a good rule to be comfortable with. We can't do a DS right here because we need this guy to have an extra negation, right? It does differ by a negation, but we need to have an extra negation. So you can do a double negation to 2 actually, and get not PA, and then you can do your DS to get to QA. Or what I like to do, just because I like MI, I think it's good to be comfortable with MI, is swap the or out for an arrow and drop that extra tilde. Like, why give yourself more tildes? Let's start throwing them away. So this is just an MI on 6. And now I've set myself up. Now I don't need any extra tildes over there. I'm happy that I have one less, because now I can just do for my last line right here, right? The last line right here. So just throw away all that extra stuff, so now we can actually just finish up the proof. So this last line right here, I actually get just modus ponens. Right, so this is going to be line 8. So that's just modus ponens 2 through 7, or 2 and 7. Oh. Right. Okay. Right. And so now, because you've shown PA really does lead you to QA, well, you've proven that PA implies QA. Right. Okay. Cool. And then, so right from there, so so that's the CP from 2 to 9 minus 1, which would be 8. And then on line 10, we can generalize line 9, because A was just a completely arbitrary guy. We can generalize line 9. So UG 9. That's what number turned out to be. So here you can see, I'll finish off just by highlighting. So the first thing we did was we noticed that we can set it up in a nice way by just saying, okay, I'm going to start with a CP with an eye towards just generalizing it at the very end of the day. So that's a good thing to be able to recognize at the very beginning. That doesn't necessarily fit into kind of this 3-stage mindset. So again, I do want to remind you, like, the 3 stages it's not some hard and fast rule. It's just generally a good tendency to be watching out for. Another great tendency, though, and in fact maybe a more important one, is to be watching out for, when can I do a CP and when can I do this generalized version of a CP where this is just a simple CP, but the idea is I'm doing it with this carefully chosen new constant, so that way afterwards I can generalize, right? But after that, but the idea is, what we did right away was we still did work in order to tear away our quantifier first. So we had to do a QN in order to get that quantifier ready, and then we were able to tear it away. And then we did old school logic, right? All of that is just old school logic. In fact, even ending the conditional proof is just old school logic, right? So that's just a De Morgan's in there that I didn't actually cite. Sorry about that. So there's a De Morgan's right in here for line 4. And so that's just all old school logic. And then finally, we ended up just needing to do one generalized rule, right? And that's where we clean it up and tack on the logic. Okay, so hopefully that gives you a good taste of how to do these proofs, and how to use these rules. Generally speaking, you still want to check, can I do a CP, or even a generalized version of the CP where you just kind of, you do a CP with an arbitrary constant with an eye towards generalizing at the very end. But other than that, a lot of the way these proofs are going to go is we're going to just start with trying to tear off quantifiers, do some old school logic in the middle, and then work by tacking on or doing some quantifier cleanup at the very end of the day. Okay, feel free to comment or email me with any questions. All right.